He showed that you just could not calculate. There was no algorithm that would allow you to calculate such bounds, I guess. Right? So, interesting comment following on from that conversion from a Turing machine or an algorithm that recognizes to one that decides. Right? Okay, now you've been hearing me using almost synonymously algorithm and Turing machine, and that will die away increasingly now, because an algorithm now, before it was a rather woolly, vague, hand-wavy sort of notion, a kind of step-by-step process to achieve some goal. The ChurchTuringThesis makes that much more rigorous. An algorithm is actually a Turing algorithm. In other words, some step-by-step process that can be implemented that can be programmed on a Turing machine. Or, and it's because of the equivalence of all these models of general purpose programmable computation, Turing machine, post machine, Church's lambda calculus, and so on. They're all equivalent, right? They all effectively have access, full access to infinite memory, and it's that characteristic that allows them to have their great power. They can, they are powerful models for computation. So increasingly we will forget about the implementation of the algorithm, in other words using a Turing machine, or the equivalent, because they're all equivalent. We're just talking increasingly just about algorithm. But remember, I keep saying this, but important to emphasize, and what's the word? Repetition. Repetition can be didactically useful, so you get the point, at the risk of it being boring or too slow. So from now on, we're at a kind of watershed, as he puts it. Sipser took out like a turning point, where we emphasize less the machine aspects and emphasize more the algorithm. So we'll be talking more and more about algorithms and less about machines, until effectively we just don't talk about machines anymore. That sort of just quietly dies away. Okay. Now we'll still talk about Turing machines to some extent. Okay. But the focus now, from now on, so that's the turning point, the watershed, like when a river splits and you're forced to make a decision. Do you go left or you go right? When a river forks. Okay. And so the focus from now on is on algorithms. So the Turing machine then is just a particular, quite a precise model for the definition of an algorithm, with the emphasis on the word precise. If you give a full formal description of a Turing machine, that means you have to specify all the states, and particularly the transition function, right, which is tedious. You have to give them all the details, every particular transition from one state to another. But it's a formal definition, detailed. It's all there, and by giving a formal definition of a Turing machine that implements some algorithm, some task, some step-by-step procedure, some set of stages to achieve some goal. By specifying the Turing machine that does it, that's how you define an algorithm. You're specifying the algorithm in detail. An algorithm is a Turing algorithm, effectively. It's implemented by a Turing machine. That's the more formal definition of what an algorithm is, and that's the ChurchTuringThesis, which Sipser did not spell out, I felt, explicitly. Well, all right. Okay, so now he's saying here, due to this watershed, this turning point, emphasizing more the algorithms and de-emphasizing the Turing machine itself. So we're not going to. There's a lot of theory about Turing machines in the literature and other textbooks. Certainly, talk a lot more at length about Turing machines and their properties, and particularly how to program them. Because it's very low-level programming of Turing machines, very tedious. And other textbooks do that, but Sipser says, going to skip over that kind of stuff. Won't spend a lot of time on the low level, describing how to program. The low level programming, very, move one square to the left, to the right. It's tedious, so he won't spend much time on that. And from now on, emphasize more the algorithms, and next session we'll start talking about various levels of description of algorithms. It's sort of like the formal level. In other words, you're giving a formal description of the Turing machine that implements that or executes that algorithm, and another level would be more the what's the technical term you used? Implementation level. So now I'm jumping ahead a bit for the next session, but give you a taste of what's coming. Implementation levels sort of at the level of detail midway between the full formal definition, where you just write out all there is about the Turing machine, particularly its transition function, the states and so on. The formal definition. The what is it? 7 Turing machine, 7 tuple. Yes, you get the 7 tuple. And the third one is high level, which is you barely even mention the Turing machine. You're not interested in the machine, how the machine implements the algorithm. You're just describing the algorithm. So using English phrases. So anyway, you'll talk about that next session. Okay. So once you're familiar enough with the nature of Turing machines, you know what they do. You've had some exposure to programming them. Very low level Turing machine programming. So once you've got that under your belt, and you're conscious that the definition of algorithm is effectively Turing algorithm. So an algorithm, strictly speaking, is an algorithm that can be implemented by a Turing machine, okay, or a post machine, or a clean, or whatever. They're all equivalent, so it doesn't really matter which label you use. Convention is you use Turing because he's sort of the most famous, because he's famous for so many other things, like the father of artificial intelligence, the Turing test. How do you know when a machine is intelligent? The Turing machine itself, the beginnings of embryogenesis mathematics that he pioneered, artificial life, and so on. No, he's just so famous. So he chose Turing to be the generic label of all these models of computation. So algorithm just equates to the vague notion of algorithm that equates to Turing algorithm. An algorithm implemented by a Turing machine. Okay, so once you're sort of happy with that, that you're quite aware that an algorithm gets implemented by a Turing machine, or its equivalent, then from now on you now focus on the algorithm. So you're describing algorithms rather than how a machine implements them. Okay.